The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, thanks for joining today's session of Cambium College. Today's speaker is Seth Poche. He's a regional technical manager and he's got years of experience in designing and deploying wireless connectivity links. So he'll be discussing RF interference and interference mitigation techniques. So feel free to ask any questions in the chat box on the right, questions or comments, and we'll get to them throughout the presentation. The session is being recorded, and we'll post it to the community shortly after. So without further ado, I'll hand it over to Seth.
I appreciate it, Colin. Thank you. Yeah, let's go ahead and get started. I'm hoping to kind of fly through this, and practicing it took me a little bit longer than it should have, so let's get going. So tonight we're going to talk about what is interference, and we're going to go over this idea of signal-to-noise ratio, and we're going to talk about types of interference as well as detecting interference. And then we're going to talk about some basic and some advanced mitigation techniques when dealing with interference. So setting the stage here a little bit, if you remember in the last session, Dave Hensley gave a great presentation on radio wave propagation and antennas and reflectors. And I stole one of his slides here where he talked about a radio and the different aspects of transmit and receive. And he said something that kind of stuck out to me, and I said, I got to steal that for this next session. He made this comment that whenever you go to transmit, the channel must be clear. And so that's what we're going to be talking about this evening, is the channel being clear. And I've highlighted there that kind of block diagram. What's there in gray, that channel, that's what we're going to be talking about tonight. So what is interference? Wikipedia has as good of a definition as anyone. And they say anything which modifies or disrupts a signal as it travels along a channel between a source and a receiver. And so here again, just like what we said in the last slide, we have a channel and we have something being transmitted and something being received. And also it's important to note that interference is a form of noise. Not all noise is interference, but all interference is noise. And I might say noise in this presentation, and for this presentation, just imagine that noise and interference can be used interchangeably. And a lot of times you'll hear that in wireless. You'll hear someone say noise instead of interference, or vice versa kind of thing. But keep in mind that there is a difference between the two, a small difference, and so not all noise is interference, but all interference is noise. And then some examples of interference in wireless. If you've ever, played Xbox, for instance, and gotten kicked out because your Wi-Fi disconnected, or maybe you're on Facebook on your phone, just scrolling down, all of a sudden everything just freezes and pauses and it disconnects, it says Wi-Fi disconnected, and then you have to wait and it reconnects. A lot of times that can be a form of interference that is causing that. If you ever drive underneath power lines and you're listening to the AM radio station, you'll notice your AM radio station will cut out. You have a wireless mouse or a keyboard and it freezes. If it's not the batteries going dead, it's probably some form of interference. And then another example is maybe static on a wireless baby monitor. These are all examples of possible interference on wireless. And I put a link at the bottom. This is a really interesting web page if you're interested in more specific forms of interference and what those different interferers may look like on a spectrum analyzer. I highly recommend going to this link at the bottom and checking out that web page. It's actually pretty incredible. And so the next thing that we need to think about when we think about this idea of a channel and a transmitter and a receiver and interference is we have to consider that interference largely only affects the receiver, not the transmitter. And so the idea is that when we're talking about interference, we're not really so much concerned about transmitters causing each other interference and making it to where they can't transmit. So for instance, if I'm standing in a room and I'm standing right next to Colin, and I happen to be on a chain smoker kick right now, so if I'm listening to chain smokers and I have my ears covered and I'm shouting as loud as I can, sing along to some chain smokers, that doesn't affect Colin. As a matter of fact, Colin could be shouting out or singing to Third Eye Blind, for instance. And, we can both, I promised him I wouldn't use Nickelback as an example, but he could be, singing out to Third Eye Blind, and we could both be standing right next to each other with our hands over our ears, and we wouldn't be affecting each other because largely interference doesn't affect the transceiver, or the transmitter, I apologize. It does affect the receiver. So if there's someone in that room that's trying to listen to me sing or maybe listen to Colin sing, obviously that would be very confusing for them. For me to be singing the Chainsmokers and for him to be singing Third Eye Blind and to be trying to pick out one signal over the other. But the interference that I would cause wouldn't necessarily affect him and his transmitting. And so that's an important aspect of interference that we need to recognize before we move forward. Also, it helps in conversation if we consider that there are different types of interference. And if we can pick apart one type of interference over another type of interference, a lot of times it will help us determine what our best path forward is to mitigate any possible interference. And so I want to introduce two ideas, two different versions of interference here. And one of them is co-channel interference, and the other one is adjacent channel interference. And so the idea of co-channel interference is that interfering radio is operating on the exact same channel or frequency of the radio you're trying to receive on. And an example of this would be if you live in one city and you're driving to another city and both cities happen to have a radio station, FM radio station of 90.1, for instance. Well, as you drive from your city to the other city, at some point your radio is going to begin cutting out on your home station and cutting over to that new station. They're both on the same channel, and now at that point, that other station is starting to interfere with your station. And we've all experienced that, driving down the road. And so that's a form of co-channel interference when both are on the exact same channel. A form of adjacent channel interference is, let's say that you're tuned to 90.1 and you're listening to a radio station. And you notice that when you drive close to this tower in town, maybe that tower is tuned to 90.3, but even with you on 90.1, you notice that when you get really close, it starts to bleed over. That signal starts to kind of invade on your channel. And that's a form of adjacent channel interference. And so we're going to talk more about co-channel and adjacent channel interference later on, but it's important that you recognize the difference between those two. And if we're going to understand interference, we also need to understand this concept of signal-to-noise ratio. And so this is a relative term. If you remember last time in the session by Dave Hensley, he introduced this concept of dBm, which is a measure of wattage. And so, for instance, you could take a dBm reading of 20 dBm, for instance, and you can directly convert that to an exact measure in wattage. And in the case of 20 dBm is equal to 100 milliwatts, or a tenth of a watt. And that's an absolute conversion. But dB, just decibels without the M, is a relative measure. And we measure SNR, or signal-to-noise ratio, in dB. And so the idea is, how much stronger is the signal over any noise that I may be hearing as well? And so if you had a signal-to-noise ratio of 10 dB, what you'd essentially be saying is our signal is 10 times louder than any noise. And it's a relative measure, because if you imagine going into a library, maybe you're going to study and you're there with a friend, there's not a lot of noise in the environment. And so maybe you could whisper and you could be 10 times louder than any noise, and the person you're there studying with would be able to hear you. And so that would be a 10 dB of SNR, if you will. Or maybe imagine that you've gone to a football game, and now everyone's yelling, and you have someone standing right next to you, and you literally have to yell to be loud enough for them to be able to hear you and understand you. Again, it may be 10 times louder, but at the football game, both the signal and the noise were significantly higher. And so I have a graph here of kind of a mock of a 2.4 gigahertz range. I'm considering kind of a Wi-Fi access point here with a 20 megahertz channel, which is that kind of block that you see. And so you see in this example, the received radio sees that signal at -53, and it sees any noise around the negative 83. And so in this case, there's a 30 dB signal-to-noise ratio, which would mean that the signal that it's receiving is 1,000 times louder than any noise. Because with decibels, every 10 that you add is a multiplication of 10. So what we're saying is this is 10 times 10 times 10 times louder. So it's ultimately 1,000 times louder than the noise in this scenario.
Hey Seth, I have a question real quick.
Sure.
If going back to your library versus football stadium example, is there any benefit to, let's say, screaming in the library when there isn't a lot of noise versus just whispering to your friend?
That's an excellent question. In wireless, and it's true in the regular world too, it's actually a detriment to scream in a library, if you will. One, they'll probably call the cops on you. But in wireless, if you can imagine, when you scream, a lot of times it's harder to control your voice. There's more often you'll see distortion, and so it's the same is true in wireless. And a lot of times when you look at wireless radios, you'll see that these higher modulations, these higher rates of communication that they're capable of, they'll actually have to turn down the power because that distortion that they inject by trying to amplify that signal actually acts as a detriment. Also, you have the effect that you can actually overpower the receiver. You know, if you're yelling so loud at someone and their ear is tuned to kind of a quiet environment, if you're yelling so loud that their ear starts ringing, well, at that point, you've overloaded it, and anything you're trying to say may not even get through because you've actually hurt the receiver. And the same is true for wireless. You can overpower the wireless receiver and cause problems too. So that's a great question. And in general, you only need to talk as loud as the data that you're trying to push through, or have as good of a SNR, or signal-to-noise ratio, for that.
Great, thanks.
Great question.
Sorry, as a follow-up, will the Cambium products that we offer, are they designed to adjust this power ratio?
They do adjust, so that's kind of a complicated question. Typically for outdoor use, you set the downlink transmit power, and that's kind of a static power that, you know, in general, what you want a lot of times for outdoor use on the downlink is you want as much range as possible. And so you set the max possible power. Now on the uplink, you run into this scenario where some subscribers are closer to the tower than others, and you don't want them overpowering, the ones that are close, overpowering the access point on the tower. And so there we do use an automatic transmit power control so they can back off their power so they're not significantly louder than someone that might be 4 or 5 times farther away, if that makes sense. So yeah, we have also when we have built into the radios that as we go up in modulation, we'll back off the power a little bit too to make sure we don't get that distortion, which is a common thing in radios. Good question, really good question. And so in wireless, we're trying to accomplish 2 things where, one, if we can increase the signal level, then that increases the signal-to-noise ratio. And conversely, if we can decrease the noise level, that also increases the signal-to-noise ratio. And so anything that we can do to make that signal-to-noise ratio better, whether it's increasing the signal or decreasing the noise, that's something that we're looking at and going to attempt to do. And also, I have a note here, you know, that SNR, sometimes you'll see things like CNR, CINR, CIR, C to I, S to I. These all are different forms of this idea of signal-to-noise ratio, and they all have very small differences depending on the band. Depending on the band, they may not use the term SNR. They may use the term CINR. But in general, if you just get this idea that we're talking about, the idea that a transmitted signal is coming across louder than kind of the environment, if you will, that's the general idea of SNR or any of these other terms as well. So just keep that in mind. And the C there stands for carrier, so carrier to noise ratio or carrier to interference noise ratio. So if we're talking about interference, we have to recognize that we're operating in an environment where we're likely to find interference. And one of the things about interference is you want to know where it is, because it may not be ubiquitous across the entire network. It may be only located in certain areas of the band, for instance. And so here are two ways that you can go out and detect interference to try to avoid it. And so the first one, this is a shameless plug. This is, I bought an E400 Cambium access point for my house, and it is amazing. And for those of you that are on this call, on these sessions, if you join the community and you go through all the classes and get an 80% on a test in November, you get a free one of these, and these are really incredible 802.11ac enterprise grade access points. And one of the features it has is this Wi-Fi detector. And so what the access point will do is it will actually turn itself into a client, and it will go out and scan all the individual channels and try to determine all the individual signals that are out there that it might be able to connect to. And then it comes back and reports what the interference is for all these different channels to help you try to tune away from any interferers. And so in this case, I see that there's some interferers kind of up the upper part of the band, and so that tells me that I need to tune my own access point towards the lower part of the band. And that's a great first step, but it doesn't exactly tell me everything that's going on, because it's only seeing wireless that's an 802.11 protocol. And so if there's some noise out there, maybe someone turns on the microwave oven, it may not see that because it's looking for that SSID, that beacon that's coming across for wireless. And so in that case, you really want to use something like a spectrum analyzer. And so I have a picture. A lot of our radios have spectrum analyzers built in. And the way that they work is they're actually tuning to small, discrete channels and measuring the amount of power coming in, and then recording that and tuning to another channel and just going through the entire band and giving you a feedback of what it's seeing as far as noise and power levels across the entire band. And so here in this example, I've marked it in red. You can see that there's a considerable amount of interference kind of on the bottom part of the band. And so that tells me that I need to try to tune my radios to the top part of the band if I can. So moving on now, going into some of the mitigation techniques. Now that we've talked about signal to noise and the different types of interference, the basic interference mitigation techniques that I put down are: 1, you can avoid the interference; 2, you can make the signal more robust; 3, you can attempt to filter the interference; 4, antenna selection; and 5, shielding. And this isn't an exhaustive list by any means, but these are some of the most common techniques that you'll run into today. So let's get started on avoiding interference. This is the number one. This is typically 99% when someone sees interference, this is what they're going to do. They're going to find where the interference is, and they're going to try to move to a different channel. But it's not always that easy. For instance, with a 2.4 gigahertz Wi-Fi access point, if you're operating on 20 megahertz channels, there's only 3 non-overlapping channels that you have to choose from. So if you're seeing interference on one channel, you're really hoping that the other 2 channels don't have interference. And so some things to keep in mind when you're going to use this technique is having a radio that has a wider band, having a radio that's able to tune to more channels. That's going to make it easier to go out and accomplish this goal of changing channels. Also, having a radio that's dual band will make it easier. So for instance, the E400 access point that you get for taking this course and making 80% on the test, it's the 802.11ac radio. It's got 2.4 gigahertz and 5 gigahertz. And so I can be on my phone in my house, and if my wife goes to heat up a bottle of milk for our kid in the microwave, and I'm on 2.4, my phone can then roam over to the 5 gigahertz. And so in that way, I'm avoiding the interference. And so that's one technique. Also, keep in mind that sometimes you don't have any control over the spectrum and what interferers are there, and sometimes you don't get that perfect chance to slide a 20 megahertz channel in between 2 interferers. Sometimes there's only 10 megahertz there, or 5 megahertz. And so if you have a radio that has other options for channels, smaller channels, typically a 10 megahertz, a 5 megahertz or more, then that gives you more flexibility and to be able to go in and avoid interference. The next technique is to make the signal more robust, and this is kind of intuitive. If you imagine that scenario that we're at the football game again and we're trying to talk to someone who's right next to us, probably the first thing we're going to do is we're going to try to talk louder. If everyone around us is yelling, we're going to start yelling. And that's equivalent in wireless to trying to increase our transmit power. And a lot of times, radios don't have this ability because we're already at the FCC regulatory limit. But that is one technique, is to transmit louder, to talk louder. The other thing we can do is we can talk slower. So if we can lower our modulation rate, if you imagine a lot of times, a football game, you talk really slow, you're like, did you see that play? That was amazing. You're not talking fast, you're talking very slow to try to increase the chance that the person listening is able to pick up what you're saying. And the other thing too is sometimes you'll repeat yourself. Sometimes you'll say the same thing in two different ways to try to help make sure that that person can intelligently understand what you're saying. And we do the same in wireless. We add error correction. We add extra bits in there for redundancy so that if an error comes across, sometimes we can correct it. And if we can't correct it, hopefully we at least detect it and can discard it so a retransmit can occur. But those are all aspects of making the signal more robust. The third thing we can do is we can attempt to filter out the interference. And so traditionally in radio design, you would typically find a fixed filter at the top and the bottom of the band that the radio is designed to work in. And these filters are designed to block out any out-of-band interference. So anything below the band or above the band that might be bleeding into your radio, they're designed to block that out. But what do you do if the interference is in band on an adjacent channel? You can see from the spectrum analyzer there on the left that the channel that we're tuned to is still being interfered with by those two adjacent channels that are in the band that we're operating on. So in this case, the static filters aren't really doing anything to eliminate the interference. So the question is, well, how do we deal with that? And one technique is to use a superheterodyne transceiver. Now, superheterodyne radios, they represent a really old technology. They're 99 years old, almost 100 years old. And what it effectively allows us to do is convert our signal, our frequency from 5 gigahertz in this example to an intermediate frequency using a tunable mixer. So we do a down conversion. We convert it, let's say, from 5 gigahertz to 1 gigahertz. And at that 1 gigahertz range, we have a very tight filter that's designed to basically wrap around the channel. So it has that limit of maybe 20 megahertz. And you can see that here. And because the mixer is tunable, as we change channels, that filter kind of travels with it. And now it's worth noting that while this may be effective on adjacent channel interference, it doesn't do a whole lot for co-channel interference because the interference passes right through the filter the same as the signal. And so this is kind of one of those things where we have to consider, okay, the interference that I'm seeing, is it adjacent channel or is it co-channel? And that kind of affects how you approach the problem depending on which it is. And so that's one way to filter out interference, and that's I put a Wikipedia. It's pretty fascinating how the superheterodyne radio works. If you have time, definitely go check that out. The next method we're going to talk about is antenna selection. This can be another great technique to mitigate interference. And that's because typically as we increase the gain of an antenna, it also makes it more directional and therefore more selective. So if you will, consider this guy in the picture with a parabolic microphone on the sidelines of a football game. even though there may be thousands of fans there cheering all around him, his intended target, whether it's a quarterback or a lineman, he's able to focus in and amplify that and bring it out, even with all the cheering and all the noise. And that is absolutely fascinating to me, that they can clearly hear what's going on, something that's happening 50 feet away with thousands and thousands of fans, cheering on at a game. But we do something very similar with wireless, and you can see to the right there, one of our antennas is a high gain parabolic dish. And so it's the same concept. It's, if we can make this highly directional, high gain antenna and we can point it directly at our source, then even if there is interference, that selectiveness of the dish that we're using is going to a lot of times eliminate that noise. It's going to increase the signal and decrease the noise at the same time. And then the last one for the basic techniques is shielding. And the idea here is that you physically want to separate the interferer from the receiver. That interfering signal, you want to try to attenuate that signal. And so, as most of you guys probably know, the one thing you don't want to do when you install a 2.4 gigahertz wireless router is stick it on top of a microwave. If you stick it on top of a microwave, you're guaranteed to have problems, because the wireless router is designed to transmit and receive signals that are operating on the range of, that 100 milliwatts or less. So 1/10 of a watt is its capability. And as most of you guys know, microwave ovens also operate in the 2.4 gigahertz range. But the microwave oven is designed to be 1,000 watts of power. And so you have this competition of the wireless router working at 1/10 of a watt with a microwave that's 1,000 watts or more. And so you can obviously see who's going to win that battle. But if you can separate the two, if you can put some walls in between the two of them, or something else to attenuate that interference, a lot of times you'll see that, people don't have problems. And as a matter of fact, almost everybody, in the U.S. has a wireless router in their home, and they probably also have a microwave oven, but yet you don't hear of all these problems that the two face. And that's because of shielding.
And to clarify,
another great...
Sorry, and to clarify, that's only when the microwave is physically cooking something, right?
That is true. That is true. So another great technique is something that a lot of WISP will do. A lot of times they'll go into a small tower, a small town as they deploy their network, and the first thing they start doing is start looking for towers. And a lot of times in these small towns, the only tower that's there is a water tower. And so they go to the city, they get permission to mount gear on top of the water tower. And I didn't get the exact picture that I wanted, but, a lot of times they'll take their antenna array, and instead of mounting on the very top like this picture, they'll mount it around the rim of the bowl there. And so what they've done is they've added, 30 feet of water and then metal on top of that provides shielding, so that one access point pointed in one direction, doesn't affect another access point that's 180 degrees off. And so that's a very clever technique that WISP have figured out, that they can go in and really have a lot of liberty when they choose channels and make sure they're not self-interfering by putting the shielding in between their access points. And then the last example is, a lot of times if you go out and you purchase, a directional antenna, a lot of times you'll find a metal plate on the back of it that's shielding to make sure no energy is coming in from the back side of that antenna, that it is blocked. And that's another example of shielding. So that's the basic techniques. And I want to go over 3 advanced techniques. And again, this is not exhaustive by any means. I mean, we could go on for weeks and weeks on some of these advanced techniques. But here are 3 that I think are interesting that we can talk about today. And so frequency hop, GPS synchronization, and beamforming.
Hey Seth, before we get too much into these next advanced topics, we do have one quick question. How would solar panels on a roof interfere with radios on either the SM or AP side? And I guess, would it interfere at all?
They shouldn't, and except that solar panels tend to be very flat. And so if you're shooting past the solar panels, it's possible that you can get reflection and multipath. But as far as any kind of interference from a radio perspective, you really shouldn't, as far as I know, get any kind of interference there. That's a good question. Yeah, you want to avoid mounting it in front of the radios, but you'll probably be okay. I've at least not heard of anyone having problems with solar panels.
Great, thanks.
Good question. So with frequency hopping, what we're trying to do is we're trying to hedge our bets. We recognize that we're operating in a band and there's likely to be interference. And what we want to do is we want to try to guarantee that at least at some point our transmission does get across. And so with frequency hopping, we don't really care where the interference is because we're going to try everywhere. And so that's kind of how it works. I have kind of a corny animation here. And with frequency hopping, what they'll typically do is they'll have very small, they'll have very small channels. So this isn't a 20 megahertz channel like before. This may only be, 125 kilohertz channel, and it's jumping around, very quickly, several times a second. And both the transmitter and the receiver know the pattern that it's taking. And so the hope and the goal here is that at some point it's going to hit one of these channels, one of these discrete frequencies that it can transmit on. And hopefully more than often than not it will be able to transmit. And some examples are Bluetooth or wireless controllers. Most console controllers, Xbox, PlayStation, use a Bluetooth chip even if they have kind of proprietary software written on top of it. Wireless mouse and keyboard, a lot of times we'll use Bluetooth. And so some disadvantages of Bluetooth, though, are lower data rates because we're not using that really wide channel. We're using a very narrow channel. The throughput's extremely limited. In fact, I think with the latest standard of Bluetooth, the theoretical maximum limit is 50 megabits, where, with Wi-Fi, we're well into the gigabits now. So much less throughput. And typically, you'll see a limited range. And I put a star by this one because it's not necessarily limited range. In fact, they have some 900 megahertz meter reading type of radios that actually have great range. But typically when you see frequency hopping, especially with things like Bluetooth, you will see limited range. So frequency hopping is one. GPS synchronization is the second we're going to talk about. And so GPS synchronization really seeks to reduce the amount of self-interference. If we consider that, I guess, so what is self-interference? Self-interference is any interference that you cause on your own network. And so possibly reconfiguring your radios, you could eliminate that self-interference. Where sometimes you deal with competitors' interference, radios that you have no control of. You can't log into them, you can't change the channel on, you just have to work around them. So GPS synchronization is a great way for self-interference. Keep that in mind to eliminate self-interference. So as an example, let's say you deploy an access point on a tower and then go out and install remote radios, we'll say A through F here, to connect to that access point. And this is kind of a typical deployment. And this is all outdoor. These are TDD radios, which means time division duplexing. That means we're transmitting and receiving on the exact same channel, just at different times. And so for our transmit here, we have it denoted as DL for downlink, and our receive, we have it denoted for UL for uplink. And these radios have fixed frames. They'll spend a set amount of time transmitting, and then a set amount of time receiving, and then they'll start over and do the same thing over and over and over again. Now, if we deploy another sector on the tower with, we'll say, radios U through Z, we can immediately see that we have a problem. The frames don't line up. So while one access point on the tower is trying to transmit, the other access point is trying to receive. And keep in mind that these remote radios may be installed 10 miles away or even more. So whenever one access point is trying to listen, and it's trying to listen to this radio that's 10 miles away, and there's an access point that's a foot away that's talking, that other access point that's only a foot away is going to overpower and cause interference so that the radio that's trying to listen to the other radio 10 miles away can't hear that weak signal. And so what this makes us do is it makes us put these access points on two different channels, and it makes us put a guard band in between the channel because there's this bleed over effect. And these radios are so close together that they'll bleed over into each other. So we might have to put 10 megahertz of abandoned spectrum, if you will, between the two channels. And so how does GPS synchronization help? Well, as I'm sure you all know, GPS uses very precise timing to triangulate position. And we can tie into that precise timing to align the frames of the radio. So now all the access points on the tower are transmitting at the exact same time, and this is similar to Colin and I singing. We're both in the same room, we're both transmitting at the same time. And we talked about how that him singing doesn't affect me singing and vice versa. And then the access points stop transmitting, and then they all listen at the same time. And that allows these weaker signals from these radios that, may be 10 miles away to come in and be able to be heard by these access points. And that timing aspect of GPS synchronization mixed with the fact that we're using directional sector antennas and then that mechanism of automatic transmit power control that we talked about earlier, all that tied together means that we can actually reuse our frequencies. One, we don't have to use any guard channels. We can put our channels right next to each other, and then we can reuse our frequency. And so if you look in the upper right, there's an example of a 4-sector site where we're only using 2 channels, and we use the exact same channel on back-to-back access points without interfering. And so why is this an advantage? Going back to that first technique that we talked about of actually avoiding interference and changing to a different channel, imagine how much easier it is to avoid interference when you only have to find homes for half as many channels. You're only looking for half as many channels that are clean. Imagine how much easier it is to plan around any interference you see. And so that's GPS synchronization in a nutshell. And then our last topic is beamforming. And so beamforming is achieved by combining elements in a phased array in such a way that signals at particular angles experience constructive interference while others experience destructive interference. And so the points that we're going to talk about are this idea of a phased array, and then constructive interference and destructive interference. Constructive interference is when we intend that 2 signals combine together and reinforce each other and become stronger. If you remember the sine waves in wireless, when those are aligned and you combine them together, it makes the amplitude of the signal louder. Destructive is when they're out of phase with each other and you combine them. You actually get what I'm going to call a canceling effect, almost like noise canceling headphones in a sense. And beamforming can be done on both the transmit and the receive, but we're going to talk specifically here about only in the receive because I think there's a really good application that everyone can relate to. So we're talking about the receive, but keep in mind that beamforming can be done on the transmit as well. So how does beamforming work? Let's see if I can pull up my slides here. Hold on. If you can imagine, this is very similar to our ears on our head. We have 2 ears, and they're spaced a fixed amount apart. Our ears aren't moving, hopefully, on our head to get farther and nearer away. They're spaced the exact same amount.
You should get that checked.
And it enables. I'm sorry?
I said you should get that checked out if it is.
Yeah, you should definitely get that checked out. And so that hopefully never changes. And yet, if you put someone in a room and you tell them to close their eyes, you can walk around that person and talk to them, and they can, even with their eyes closed, point to where they're hearing that sound come from with a high level of certainty at that. And so you have to ask yourself, well, how can we do it as humans? And the answer is that there's a delay between when the noise hits one ear or when the signal hits one ear compared to when it hits the other. And so in this example, someone's speaking to the left of the person listening. And so that signal hits the left ear before it hits the right ear. And so there's that delay. And it's the exact same signal that both ears are hearing, but they're offset. And in wireless, we call that offset a phase shift. And what our brain does is our brain takes that delay and it offsets for it, it compensates for it. You know, if there's someone to our left, you don't hear an echo because you heard two individual signals. Your brain actually takes those two signals, it compensates for them, and then it combines them together. And the same is, can be true with wireless with beamforming, where you have two individual receivers. They're spaced apart, similar to ears, and it's a set amount of spacing. They're very precisely spaced. And as we receive, we can take those two and we can compensate. So let me go over that one more time. So in wireless, we call that delay a phase shift. And once we've determined the phase shift that's occurring between two signals, we can then adjust for that delay in the future. So in our radio electronics, we can actually implement a phase shift in circuitry to put both signals in phase again. And then once both signals are in phase, we can add them together, and the two signals become constructive. The end result is the combined signal is louder and clearer than either of the two were individually. And this phase shift that we do also has this effect of noise canceling type phenomenon that I mentioned earlier for any signals that aren't, or that happen to be coming from a different angle than the one that we're tuned to. So the combination of any signals becomes destructive at that point. In essence, we're creating a beam of directed listening to a specific area. So let's look at how that might work with outdoor radios, for instance. In a typical sector without beamforming, our signal is received at the receiver along with any interference that's generated. That interference is noise that decreases our SNR. But with beamforming, we're able to create 3 different beams by applying a different phase shift to the signals that we are receiving. And each of the beams has the effect of increasing the gain to our desired location and at the same time attenuating the signal for anything else it receives. And in this example, the interference is attenuated while the signal is increased, which improves signal to noise ratio. And that's what we talked about. You know, anything we can do to increase the signal, anything we can do to decrease the noise, you know, beamforming does both of those things. Now, the really exciting thing about beamforming is that it's not limited to just 2 receivers like ears on our head. You know, we only have 2 ears, and so in our example, we're ever only going to be able to combine 2 signals. But with radios, we can implement a radio design with maybe 4 receivers or 16 or 256. And as you add more and more transceivers, you do 2 things. You, again, increase the gain of your intended direction that you're beaming towards, and you also decrease the signal of any interferers outside of that beam. And this is kind of what we're starting to see. The price of all the electronic components is dropped, and it's easier to make radios that are affordable. And so we're starting to see these massive deployments of beamforming where there's radios with a lot of transceivers built into them. And this is actually one of the fundamentals of the MU-MIMO that we use in another platform that we have. So that's it for me. I guess we'll turn it over for any questions.
Yep. There aren't any right now, so if you guys have any last-minute questions about the presentation or about our radios in general, we'll be glad to answer them. So I'll give you guys a few minutes. Oh, here we go. With the PMP 450, we don't have the option for channel hop. Are you talking about the active interference, Sean? The active interference filtering?
As far as I know, with the 450, the only channel hopping that we do is in the 365 range, where we have listen before talk, and if we notice that there's someone interfering on that channel, we'll jump to another. And then also with DFS in the 5 gigahertz range, we'll change channels for radar detection, but those are the only 2 that I know of.
And I guess I'll add on that the 450i and as well as the 450m does have the dynamic interference filtering.
Right. Yes. Exactly. Yeah.
Yeah. Yeah. Then if you use the 450i, you should be good in that regard. So as we wait for any last minute questions here, since some people might have missed my plug at the beginning, I just wanted to reiterate that this session will be or is being recorded, and it will be available for rewatch on our community page. And so you could always, we'll also have Seth's slides available as well. So here's a question. What is our opinion between the EPMP 2000 versus the 450i?
So with beamforming, with regards to beamforming, today EPMP 2000 only does beamforming on the uplink, and so as they're building on, it will become more advanced. But the 450i, I'm sorry, 450, was that M or I? That's 450i. I got you.
They have.
Yeah, that's a good question. So the 450i has the filtering built in. The beamforming can be nice, but it can be tricky if there's multipath, and so the access point thinks it knows where the SM is, but the SM, that location seems to change. And so the filtering in the 450i, in my opinion, can be a little bit more stable because it's something that's very static and consistent. But it is hard to compare the 2. They are very much different technologies.
Yeah, and just to add, in general, the 450 platform is our carrier grade platform. For if you need the more, weatherproof, if you need a higher encryption rating, things like that. We do have another question here. Did I just hear 365 and 450M? I think we might have perked your ears. In particular, we were talking about the 450i. That would be a question I believe you would want to ask our product manager for. I don't think we have the specifics, if I'm not mistaken. Can we explain GPS sync through, i.e. auto sync free run, and generate sync PMP 450?
Sure. So, we talked about GPS sync, and we talked about how critical it is that all the frames at a tower and a network are lined up so that they're transmitting at the same time and receiving at the same time. But, GPS isn't always reliable. Sometimes, a storm might come through or something, and you can lose GPS. And so the idea is, do you want your radio to turn off at that point if it loses GPS so that it's not causing interference? Or would you rather it keep operating? Maybe it's going to cause interference, or maybe it's out in the middle of nowhere and there are no other radios that it can interfere with. And so this idea of auto sync and auto sync free run and generate sync is how the radio responds if it loses the GPS sync that it needs. And so auto sync free run says use the GPS sync, and if you lose GPS sync, start using your own timing. And it can be accurate for some extended period of time. I'm not sure exactly. And then generate sync says even though you may or may not be getting GPS sync, I want you to go ahead and just create your own sync. At that point, you have to use very careful channel planning to make sure you don't cause interference to yourself.
Let's see.
I hope.
Oh, yeah. If that didn't answer your question, you could always clarify again. Is beamforming only available for certain radios, or can it be set up with any radio?
Right. So it is only available with certain radios, and some of that is it has to be designed for the radio, because one of the things you have to have is you have to have multiple receivers at a minimum, and they have to be separated by a set static amount. And so it's not like you can just go out and buy two antennas and hook up two antennas to one access point and expect to have beamforming. It's something that's built into the radio to be able to do that.
And which method is better for longer range and higher bandwidth, GPS or beamforming?
That's a good question. I think of them as two different things. I think of GPS synchronization as a way that you can best use the channels that are available. And so, for instance, if you can find a channel that's cleaner and you can reuse that channel, and maybe the noise floor is 20 dB greater than another channel that you would be forced to if you didn't use GPS synchronization, then in that case, GPS synchronization will be better than beamforming, because your gain for beamforming, I think now, is at most about 10 dB. And so GPS synchronization is basically helping you find cleaner channels in a sense. So it's a tough question, but yeah.
And let's see, which is hold on. What is your opinion about horn type antenna versus sector antenna?
I think typically for point to multipoint, the go-to is that you put a sector antenna for the access point and some kind of parabolic antenna for each of the subscribers. And I think the idea there is typically access points can be more expensive, and so you want to make sure it's got kind of this wide range. You can theoretically use, these high-gain parabolic dishes for the access point, but you'll have a very narrow sector. It may only be 5 degrees, 10 degrees wide, and so if you want to cover around the tower 360 degrees, you may be looking at, quite a few access points in that scenario. So typically my preference is sector antennas at the AP, at the tower side, and then parabolic dishes for any remote is my preference.
So I think someone is just commenting that there are some horns that have 90 degrees sectors and no null zone,
Gotcha.
RF elements.
Yeah, and I'm getting a little bit outside of my expertise there. Last time I checked, I thought that the horn antennas had a little bit lower gain. They have excellent interference from the side rejection. They reject interference from any side sectors, I've noticed. But yeah, when I was speccing them, I think they had lower overall gain compared to a typical sector. But maybe I'm out of date on those.
All right. Well, that looks like that's all the questions. He said, "No, you're good."
Awesome.
Great. So, if you guys don't have any more questions, I guess that we could wrap it up. Seth, do you know if there's another Cambium College session after this one?
Oh, there absolutely is. I believe it is is it 2 weeks?
I'm not.
I would have to look.
I'm not entirely sure, but I think it might be. Oh, here, actually, we did get one more last-minute question, and technically we have to the top of the hour, so if you guys have any more questions, be sure to get them in real quick. But should you add the antenna gain in an SM for better power management, or is it auto just as good? Does distance have an effect?
So distance absolutely has an effect. If you remember what Dave Hensley talked about last time with free space path loss. Distance is greatly going to diminish the receive level at the access point, and then vice versa. As far as adding the antenna gain, for Cambium products, the way that it works is the access point is actively listening to each individual subscriber, and it's monitoring, and it doesn't know what that antenna gain is as that signal comes in. All it recognizes is that it came in too hot, and so it tells the subscriber to back off its power. And so I would say you should always put your antenna gain into the radio so that you comply with regulatory requirements. But even if you didn't, the radio, the access point, it wouldn't affect how it tells the SM to back off, and it would still tell it to back off the right amount. I hope that helps.
Yeah. How about when you need to have facing radios? Can you put them on the same channel even if they're spaced out, let's say 20 miles with a 4-mile gap, the broadcast limit?
So it's preferable that you don't have two towers facing each other that are on the same channel. But whenever you do have subscriber modules, and this goes back to that idea that without the proper shielding on an antenna, you can actually get signal from the back. So one SM that's pointed towards a tower could actually be receiving a signal from its backside of its antenna, and it could interfere at that point. So it's preferable that you don't do that, but in situations like this where it is 20 miles away, and especially if you use high gain antennas that do have shielding on the back, I have seen that where that's worked, so it is possible.
All right. So let's give it just another 30 seconds or so, just because sometimes the questions stagger in. Okay. Okay, so it looks like we're finally out of questions here. So I just wanted to thank everyone for joining again. Thanks, Seth. It was a great presentation. And and you know what? Let's just answer this one last question. Any chance to use real radio interfaces in future classes to show a real-world example, i.e. show SNR on a radio and how to interpret?
Yeah, absolutely. That's great feedback. Yeah, we can definitely do that. We have the radios.
Yeah, perfect. All right. Well, with that out of the way, thanks again, Matt. I'm sorry, Matt, for the question. Thanks again, Seth, for the presentation. And I'll see you guys on the next Cambium College session.
Thanks, guys.